everything about Lattice QCD after today. All right. So, it's going to be an ambitious day. We are almost done talking about one-body stuff. So we're going to finish that up, and then we're going to talk about, this is a few-body school, right? I will wave my hands and say, just go to larger numbers of particles, it's fine. All right, so what did we do last time? We showed that the things we're interested in, correlation functions, how do we get them from the lattice? We compute inverses of the Dirac matrix to give us propagators. We also compute determinants of the Dirac operator to give us part of the partition function. From this, we get a probability distribution for our fields U. We sample this with Monte Carlo. We compute observables, which are inverses calculated on whatever set of field configurations you have. And then somehow this becomes something we can use to interpret physics from. So that's what we're going to talk about today, is how do we get physics from this. But first, I'm going to have an aside. We're going to talk a little bit more about this M inverse, because related to everything you're learning about S-matrix theory and poles and physical states, right? Those are things that we get from propagators. We look for poles in the propagators, and that tells us what the physical states of the theory are. So we want to look at the lattice version of this propagator and see what are the physical states. And we'll see that they're not exactly what we want, and that's a problem. All right, so I'm just going to look at the kinetic part of the fermion matrix. So this would be the kinetic term if we had a free fermion, so non-interacting, in the chiral limit, so the limit that the mass goes to 0. And remember that in that limit, it's called the chiral limit for a reason. When you take the mass to 0, you should have chiral symmetry. So we expect that the kinetic part of the fermion matrix should obey chiral symmetry if it's actually describing QCD, which is what we're aiming to do. And remember that we wrote it, all right, let me try not to use squiggles. I'll use lots of squiggles today because I don't like working out factors of 2 and minus signs, but I'll at least start with an equal sign. So the action in the continuum is this. Okay, but then we discretized this derivative in order to put it on the lattice. So this thing, when we discretize it, this integral becomes a sum. So if we discretize the integral, it's a 4-dimensional integral. So this is 4 times basically the width of our intervals inside our integral. And then we sum over x in all directions. And I'm going to explicitly write the sum over mu. It is a repeated index, but I'm going to keep this around because it'll be convenient later. I might forget it, so you can yell at me if I do. So when we discretized it, this is what we got. So the derivative became this finite difference. I'm writing it as x plus mu hat, so that's 1 unit in whatever direction mu you're taking the derivative in. But we want to write it in the form of something like this, because this is the thing we worked with yesterday, and we found that the propagators were inverses of this matrix. So I need to translate this thing into psi times the matrix dotted into psi. So, and I'm going to do a slightly different derivative than the one that we derived. This was the simplest one with nearest neighbors. Yeah. Is there a what? I'm sorry. A bar. Thank you. Yeah, so rather than using nearest neighbors, I'm going to make it look a little more symmetric. It's just nicer to work with. And take the difference between two adjacent sites. So I'm going to go from x plus mu to x minus mu, and then divide by 2a. And I'm allowed to do that because in the continuum limit, it approaches the same thing. But it just makes the math a little bit nicer. All right, so this thing then goes to 1/2, because I'm going to divide by 2a. I'm going to pull this a out front, and I get 3 powers of a. I have my sum on mu, and then a sum on x prime. And then what I get from here are just some Kronecker deltas. So delta onto the next board. So this thing, when it acts on the size, pick out the components x plus mu in one term and x minus mu in the next term. But now this thing looks like something of this form. And I can recognize that this is a matrix that depends on x and x prime. All right, so if I want to invert it, what do I do? How do we invert matrices? How do we do anything with matrices? What's the easiest thing to do? Make it diagonal, right? That's what we do in quantum mechanics. We pick a basis in which our matrix is diagonal, and then the inverse is easy. All right, this is just a kinetic term. It's a derivative. So in the continuum, it's diagonal in momentum space. It's going to be the same thing on the lattice. But rather than using a continuous Fourier transform, we have to use a discrete Fourier transform. So for some general function, our Fourier transform is a matrix acting on our original basis, or our vector in the original basis. And I just have a sum over some discrete allowed x's. And this allows an identity, or rather, there's an identity, because this is a complete set of states, that this guy So if I sum all of my plane waves, I get a Kronecker delta. All right, great. So I'm going to take the Fourier transform of this thing. This thing has, it's in a position space basis. It has two indices. I Fourier transform it by acting on it with this matrix on either side to Fourier transform each of the spatial indices into momentum indices. So in momentum space, we get this. And then we get one on the other side. So this one acts on this one acts on this index, and turns it into K and L. And since I'm applying it on both sides, I have the Hermitian conjugate acting on one side, and that's why I have a minus sign in the exponent. All right, so using this for our M, I'm going to go ahead and sum over my x prime, because the only place that x prime comes into it is in these Kronecker deltas. So when I sum over x prime, I'm going to have one term where I set x prime equal to x plus mu, and then another term where I set x prime equal to x minus mu. So I'm just going to go ahead and do that. All right. So I plugged, yeah, I do have my gamma mu. Hey, look at that. I plugged that thing in and then performed the sum to set x prime equal to the things in the Kronecker deltas. Hang on. This is a minus. That's important. Okay, so we have this overall factor that we can pull out front. And then all we're left with are these mu hats. When we dot L into mu hat, that just picks out the mu component of L. So I'm going to get an L mu from dotting this thing. So I get E minus 2 pi I minus, and then I have the opposite sign on this term. All right, two things to note. One is I have a sum on x, and I can combine these things to be this, and I'm summing on x. That looks a lot like this. It doesn't matter whether the thing I'm summing over is x or k in the exponent, because they act identically. So that will give me a Kronecker of KL. It tells me that K minus L has to be 0. So this thing, once I sum over X, gives me a delta KL. And then what does this thing look like? A sign, right? And there's an I, and I think maybe a minus sign, because, you know, this term should be first, maybe. Yeah, I think so. All right, but we don't care about overall signs, because we're going to look for poles. That's the important part. All right, but let me just write it explicitly. So I think it's minus. Somebody correct me if I am wrong. We've performed the sum over X. This is actually twice the sign. So we get rid of this factor of 2. There's an I. Let's do this first. Okay, no. That's a mu. My mu's are terrible. All right, and then we have a delta KL. And this thing is M in momentum space. So the first thing we see is it's diagonal, which is good. That was why we went to momentum space in the first place. And it has this dependence on the momentum, K. This is pretty different from what we would expect in the continuum, right? If we Fourier transform this thing, we would just get K mu dotted into gamma mu, so we would get something like K slash coming from here. We don't quite have that. We have the sign of K. But remember, we're only going to get QCD in the continuum limit. We can't get an exact derivative until we take A to 0. But where is A in this thing? Let me define. Somewhere I have it. Maybe. Yes. All right, let me define K mu, or sorry, Q mu. There we go. To get rid of this 2 pi, and we also want to, we should be worried about this thing. What are the dimensions of this thing, right? So let's put in explicit powers of A to make this thing dimensionless. So then this sign becomes sign of QA, or K, yes, QA. Yeah. All right. So now this thing has the correct dimensions of momentum, the thing that we expect it to be. It's multiplied by a power of A in order to make the argument of the sine function dimensionless like we expect. And now I can expand this thing for small a. So for small a, we just get Q, which is what we expect in the continuum, plus dot, dot, dot. All right, so the whole point of diagonalizing this thing was because we wanted to look for poles in the propagator. So poles in the propagator, we've now diagonalized it, so the propagator is just going to go like 1 over this thing. So poles are going to correspond to when this thing is 0. For a massless non-interacting fermion, we expect that pole to be when Q equals 0. That's where the physical propagating state is. And good, we have that. When Q is 0, the sign is 0, and we get the propagating state that we want. However, we have to be a little more careful. We did this Fourier transform. I didn't really specify what the sum is over, right? What are the limits of this thing? When we discretize the theory in position space and then go to momentum space, that momentum space becomes periodic. And the range of my Q's is over what's called the Brillouin zone. If you've ever had condensed matter, right? We know that momentum space of a lattice looks like a periodic Brillouin zone. So this is the range of my Q's. So what's the problem here if we're looking for zeros of the sign? We already said there's a 0 when Q equals 0. What else happens when I consider this Brillouin zone? Are there any other zeros? So there's a less than or equal to on one of them, right? What about when it's equal to pi over a? What happens to the sign? It's 0, right? If I didn't have this pesky, if I just did this, then we'd be fine, right? But it has to go all the way up to pi over a on one edge or the other. And so you're going to get another 0 at the edge of the Brillouin zone. The edge of the Brillouin zone, when Q is pi over a, and you take the continuum limit, a goes to 0, this is a very, very large momentum. So we have two poles in any given direction, because there are 4 that we're taking here. So you have 2 possibilities for a pole, and there are 4 directions that you can have these poles in. So there are 2 to the 4 combinations of poles that you can have inside this Brillouin zone. So we don't have one propagating fermion, which is the thing we were trying to construct. We have 16. So now we're starting to sound kind of like string theorists, where we're like, well, maybe 11 dimensions will work. I don't know. Seemingly random number, 16. So 15 of these things are non-physical, but they're there in our lattice discretization. We have to get rid of them because they're not actual states in our theory. There's another problem, which is, so if we had one propagating fermion, we could define it to be, say, a left-handed fermion. And remember that chiral symmetry requires that you can perform a transformation on left-handeds and right-handeds independently and still have a symmetry. Here we have an even number of states. This even number of states comes from a shift symmetry. So this is our dispersion relation. This is symmetric if I take Q to minus Q up to a minus sign. I can absorb that into my definition of gamma mu's. So I can say that for every state Q, I also have a state minus Q that transforms under minus the gamma matrices. So some new set of gamma matrices which are the same as the old ones up to a minus sign. So In particular, gamma 5 goes to minus gamma 5. So that's like flipping the spin or the handedness of our particles. So for every state Q, I have one that is minus Q and transforms under minus the gamma 5s. So there are left and right-handed partner states. So these 16 states describe 8 left-handed particles and 8 right-handed particles. And they're coupled to each other via this symmetry. So you can no longer rotate them independently. You can no longer define just a left-handed fermion and perform a transformation on it. If you perform a transformation on that, you also have to perform a transformation on its right-handed partner. And so we only have a vector symmetry remaining here. So chiral symmetry on the lattice, big problem. In fact, there's a whole no-go theorem that says you just can't do it. You can't discretize QCD in 4 dimensions and retain chiral symmetry. And I talked to you a lot about how important chiral symmetry is for QCD. Even though it's broken, it has imprints on the spectrum, all these things. So there are 2 problems. One is we have to get rid of the extra 15 states that we don't actually care about. That's a must-do. The other is, what do we do about chiral symmetry? Do we say, well, I know when I take the continuum limit that, say, the right-handed partner states might go to infinite momentum and decouple, and so I get chiral symmetry in the continuum limit, so do I care that I don't have it in the discretized version? Maybe, maybe not, depends on what you're calculating. So there are lots of different ways that people have come up with for getting around this problem. The simplest by Wilson was to add a term equals this thing plus an extra term that looks kind of funny. So R is a constant. It's just some number that you can tune. And then we have this 1 minus cosine. So what happens is when Q is near 0, this term is what? 0. So it doesn't do anything to the physical pole, the one that we want, the one near 0. But when Q is near pi over A, what happens? It becomes 1 or R over A, right? So the states near the edge of the Brillouin zone pick up an extra constant term. So a constant term is like a mass. So the ones near the Brillouin zone pick up a mass that goes like R over A, and if A is small, it's a very heavy particle. We say if A goes to 0, the mass goes to infinity and it totally decouples from our theory, so it doesn't matter. So this gets rid of the extra doubler states, but it completely breaks chiral symmetry because it's like a mass term. And remember, a mass term breaks chiral symmetry explicitly. So even when the physical mass parameter that you put into your Lagrangian goes to 0, there's this extra mass term. It breaks chiral symmetry, but maybe we don't care because we know we get it back in the continuum. That's one way of doing it. These are called Wilson fermions, or if you see things like Clover fermions, they're all breaking chiral symmetry in this way. There are other ways to get around it. The no-go theorem is for 4 dimensions, so one solution is to go to 5 dimensions, where you actually can have chiral symmetry. This is called domain wall fermions. So in that case, you have a nearly exact chiral symmetry, but now you have to compute in 5 dimensions, so your computational time might go up. So people choose different discretizations, different ways of dealing with this problem based on computational time, how much does chiral symmetry matter for a given observable that we're looking at, et cetera. There's also something called staggered fermions, which is kind of bizarre, but it works. And they're super fast. So people use those when they just need fast computation time. All right, so questions about this? Mm-hmm. Yeah, yep, exactly. This doubler problem and the chiral symmetry on the lattice problem go hand in hand. All right. So let's see how far we get. So for the rest of today, we're going to talk more about correlation functions. How do we get physics out of them? I want to very briefly wave my hands and talk about Wick contractions, which Andre brought up in one of his lectures. So what kinds of correlation functions can we write down? So a correlation function is an expectation value of, say, some quark fields. Nope. And when we write expectation value, we're talking about in between some particular states. Those states are always assumed to be the vacuum. So if I write brackets with no states in them, I mean a vacuum-to-vacuum expectation value. So the simplest thing I could write down would be this. This would be a quark propagator. I know I would pull down an inverse of my fermion matrix. However, there's an issue with this, which is that it's not gauge invariant. And that is related to the issue that calculating a correlation function of quark to quark, we don't have asymptotic quark states in QCD because of confinement. So this thing is not what we would call a physical observable. I'm a nuclear physicist, so the things that I'm interested in calculating are, say, masses of particles that exist at 0 temperature. So something I might look at would be an expectation value of, say, a proton. So this thing, if I construct the color indices properly, I can create a color singlet. And this is a physical observable. This is the amplitude for creating a proton at some point and annihilating it at some other point. All right, so we did these path integrals for some correlation function involving a single fermion field. Now we have this problem of identical particles. So for example, my U quarks are identical, so I have to add all possibilities, all amplitudes. So how do we do this? If we're integrating, so this expectation value implies that we're integrating over all of my DD, whatever, context, right? This is my D quark, my U quarks. So I'm performing this integral, this path integral. And I told you that these things are non-zero whenever you have, in this case, a U bar U pair or a D bar D pair. But there are different ways that I can form these pairs. So I know that if I integrate over my D's, for example, these guys will give me an inverse of my D matrix from x1 to x4. But there are two different ways that I can combine my U's and my U bars. So if I write it the way I wrote it here, then I do my inner integral first. So I can move, say, this one over, and then I have a UU bar pair, and I can perform that integral. That would give me an M inverse of my U matrix from x3 to x6. And then what's left over, if I move this one over, I get an M inverse U x2 to x5. But I could have also, instead of moving this one over to perform this integral, I could have moved this one all the way over and performed that integral first. That is essentially like taking these two and flipping them. So I get a minus sign when I do that, because they're fermion fields. So I get two possible terms from this. I get this one minus, so the D can only connect to the D, but I can connect this guy here and this guy here. So then I'll get a mu inverse x2, x6, a mu inverse x3, x5, and then md inverse x1, x4. So this would be the correlation function that I would compute for the proton. And these are called Wick contractions. You'll learn about them in field theory. How do you connect the different fields in order to construct propagators out of them? All right, so finally, now that I've constructed a correlation function that corresponds to something physical, what is that physical thing, and how do I get it out of this correlation function? And why the hell did I go to Euclidean space in the first place, right? That will finally be revealed today, other than, as I mentioned before, positive probability weight. This is a different way of looking at it, so I'm just going to look at it in operator state formalism, so think quantum mechanics now. We're just going to compute expectation values. So if I have my correlation function, it's a function of time. I typically will want to create them at some time t equals 0, and then annihilate them at some later time to see what is the amplitude for propagating from 0 to t. I'm going to combine these guys into something that I just call P of xt. So this, or P bar, this thing creates these three quarks, combines their colors in such a way that you get a color singlet, combines their spins in such a way that you get a spin a half particle. So I'm suppressing a lot of indices here. There are going to be a lot of gamma matrices and Levi-Civita tensors that combine all of your indices in a good way, but I don't have time to go into that. So my C of t I'm going to create a proton at time 0 using those quark fields and then annihilate it at some later time t. And I want to look at the vacuum expectation value of this thing. And let me explicitly put in my vacuums, because now we're going to talk about operators and states. All right, so first off, these two operators are acting at different times. So I can't really directly take their overlap with each other because they exist at different space-time points. So first, what we want to do is translate this guy to be at the same time as this guy so that I can then look at their overlap. So in quantum mechanics, how do I do that? I have an operator, and I want to time evolve it, so I just use the time evolution operator. However, this is the time evolution operator that we know and love from quantum mechanics. When we go to Euclidean time, we take t to minus it. Maybe there's a minus here. Depends if you're time translating forward or backward, whether you have a plus sign or a minus sign. But the point is that we get rid of the I. So I have this. I need to time evolve this thing. So I apply, it's an operator, so I have to apply the time evolution operator and the left and the right. This is, what, the Schrodinger picture? Yeah. Quantum was a long time ago for me. All right. Okay. So I have time evolved these things. Note one thing. This operator is acting on a vacuum state with my Hamiltonian. So what do I get when I act with the Hamiltonian on the vacuum? The ground state. So if it's the vacuum, we always define our vacuum energy to be 0, because we always define energies relative to the vacuum. It's probably infinite, but infinity minus infinity is 0. We do that all the time. So this acting to the left gets me a 0 up here, so it's just 1, this operator. So I don't have to worry about it, it goes away. Okay, now what do? We have a Hamiltonian. We have some states that are not eigenstates of the Hamiltonian, because my operator is just something like this. The proton is not 3 quarks. All right, you are told a lie. The quark model says it looks like it has the quantum numbers of a U, and a D, but this is a totally non-perturbative thing with glue and QQ bar pairs and all this other stuff dressing these things. So if I just have an operator that creates a U, and a D, it will have the right quantum numbers to create a proton, but it also has the right quantum numbers to produce a whole tower of other states. For example, it has the same quantum numbers as this, which looks like a proton plus a pion. And this, right? I can write down an infinite number of things that have the same quantum numbers as my operator. All of those physical states, so say a proton and a pion with the right quantum numbers, those are the eigenstates of the Hamiltonian. They have some overlap with the operator that I'm using to create my proton, but none of these pure quark objects are actually eigenstates. We don't know the eigenstates. If we did, we wouldn't have to use Lattice QCD. We'd know them. So what do? What do we always do in quantum mechanics? We insert a complete set of states. And usually we like to insert a complete set of states that diagonalize our Hamiltonian. So I'm going to insert complete sets of energy eigenstates. I'm going to put 2 of them in here. So M and N denote which energy eigenstate I am looking at. I have the vacuum. I have this guy acting on it. And here, I'm inserting 1. And then I have this operator. And I'm going to insert 1 again. And then this. OK, so what does this say? This says, what is the overlap of the mth energy eigenstate with my operator P? And then project that onto the vacuum. This is just a number. It's the overlap between an operator and a state. So it's like some probability amplitude. It's a number. Let's call it A sub m to denote that it relates to the mth eigenstate. This guy is also just some number. A sub n, let's call it dagger since it corresponds to a p bar overlap. So these are just numbers. What about this? What does this give me? Energies, right? When the Hamiltonian acts on n, it gives me E sub n. So this is just some number now. And then I have this. This is 1 if m is equal to n. They're orthogonal states, and it's 0 otherwise. So I get a delta. So this delta can get rid of one of my sums. So this whole thing goes to sum on n this. This is just some number that tells me how good of a job did I do in using an operator to have overlap onto the nth energy eigenstate. And these are just exponentials. And they're exponentially dropping with time. This looks a whole lot like a partition function. If we didn't have these amplitudes multiplying each Boltzmann factor, it would be a partition function. This guy is helping us project out particular states within that partition function, having some probability. So, if Euclidean time is our proxy for inverse temperature, what happens when I take t to infinity? That's like taking temperature T, capital T, to 0. We get the ground state, right? When you go to 0 temperature, only the ground state survives. And you can see that mathematically because this is a sum of exponentials. If t is large, the term that's going to win in the end is the one with the smallest thing multiplying time. Because we want to make this as small as possible in order to make this as big as possible. So if we go to large time, large Euclidean time, we just project out the ground state, which have the quantum numbers of whatever operator I chose. So if I chose something with the quantum numbers of the proton, The ground state energy is just the mass of the proton. And this is how we get it out of these correlation functions. We do this, we compute quark propagators on some set of gauge field configurations. We get it as a function of time. You plot that function of time and you fit it to go to large time, because we can't actually go to t equals infinity for multiple reasons. You fit it to an exponential or a sum of exponentials, and you pick off the ground state. You can also, in principle, pick off excited states at smaller times if you do a multi-exponential fit. You can also do a more sophisticated job if you want to save on computation time by not. So if you make t very large, obviously your computation time is going to scale with t. There are other issues with going to large time, which I'll talk about in a second. But first, consider so we have this at hand, right? If my A0, which represents the overlap of my operator onto the ground state, is small, then I'm going to have to go to very, very large times before this term dominates and I can pick off the ground state. So I want to make this as large as possible. And in particular, I want to make it much larger than the overlap onto all the higher excited states, so that those things will die off more quickly and I don't have to go so far in time. That's hard to do. It's really hard to engineer good operators because we don't actually know what the proton looks like. But what I can do is use more than one set of operators. I can construct two different proton operators that have the right quantum numbers but have maybe different spatial dependence. I can try to think of, well, maybe the proton doesn't look like quark sitting at one lattice site. Maybe it looks like something smeared over a Fermi size. That's something that people commonly do. And you could maybe consider different smearing radii to try to get different overlaps. So let's say my first, no. So let's say I have correlation function 1 using operator 1 that gives me some overlaps A1, B1 onto the ground state in the first excited state, and there's also a whole host of other states. I can take a second operator that maybe has different smearing, or maybe I can somehow project onto a plane wave. There are lots of different things you can do with these wave functions. But if they have the same quantum numbers, they're gonna have the same energy spectrum. They're just gonna have different overlaps onto the different states. But the E's are the same if the quantum numbers are the same. So I could imagine constructing a linear combination of these operators in order to eliminate this first term that gives the first excited state that we don't want. So I could do something like B1 over, I could construct something like this. I can either just take these correlation functions and get this function, or I could take the operators that give me these and construct this linear combination. And that gives me some different overlap onto the ground state, but it has no overlap on E1. So this one goes away. So the next term that we get will be of order the second excited state energy. So this is like the improvement of our lattice action, right? I can improve my operators, my correlation function, by taking linear combinations of operators that eliminate the first systematic error that we don't want to have. And then we only have to go far enough out in time that this one dominates over this one, which is much, much smaller than this term was. You can get even fancier. So this is a linear combination of operators that maximizes overlap onto a particular state. You can imagine taking a whole bunch of operators and creating a matrix of correlation functions for some set of operators, and then diagonalizing it to get the right linear combinations that overlap onto the ground state, first excited state, etc. I can't go through it, I don't have time, but you can imagine this process, right? Diagonalizing a matrix to get eigenvalues is equivalent to finding the proper linear combination that gives you the best overlap. So this is called GEVP. Sometimes you'll see it in literature as variational principle. It's kind of similar to a variational principle in quantum mechanics. But the state of the art for getting these energy spectra is this, where you use a large number of operators and you form a matrix and diagonalize it and you get your spectrum. And then we give it to people who do S-matrix theory and they, in a finite volume, etc. Okay. Why am I so concerned about not going out to large time? It's not just because I have to make my lattice bigger and that costs more numerically. There's a larger problem, which is that we are not performing these integrals exactly. We're doing Monte Carlo. We're only getting some finite set of configurations, and that's going to have statistical uncertainty associated with it. So in principle, as you increase the number of configurations, the central limit theorem holds. So the statistical uncertainty will go like 1 over the square root of the number of your configurations. But that's multiplying something. So let's think about what that something is in my last 2 minutes here. And in particular, if we're doing nuclear physics, we are looking at protons and neutrons, and we want to look at multiple protons and neutrons so that we can get scattering and things like that. So let's just think about a correlation function of a proton. And I'm going to draw a picture and wave my hands and say that this correlation function looks like 3 quark propagators that are being averaged over my set of field configurations. So I'm going to draw it as an expectation value of 3 quark propagators. Okay, so what is the error on my mean if I take a finite sample size? Central limit theorem says it should approach a Gaussian with width that goes like the variance of the operator. So I have to figure out what is the variance of this operator. And these quark propagators are complex matrices. So if I look at the variance, I'm going to have twice as many of them because I'm squaring the operator. So think about this like this is some operator. The variance is going to have a term that goes like magnitude of operator squared. So I'm going to have 3 quark propagators. When I take the dagger of a quark propagator, I turn it into an anti-quark propagator. So I'm going to draw that an anti-quark propagator as like 3 lines going backwards. This is just another correlation function. It has 3 quarks and 3 anti-quarks in it. It should obey a spectral decomposition and go like e to the minus energies. And at large times, it will pick off the ground state of a 3 quark, 3 anti-quark state. What is the ground state if I have 3 quarks and 3 anti-quarks? It's the lowest energy thing I can construct out of that. It's whispers, muttering. What does a quark anti-quark look like? What kind of QCD object? Pions, right? And pions are the lightest thing in my theory. So as I go to 0 temperature, these things will form 3 pions. So this thing will fall off like 3 times the mass of the pion times t. So if I want to look at the signal to noise ratio, that's what really matters. The signal is this guy. It goes at infinity. It's going to fall off like the mass of the proton with time. The noise is going to go like the square root of this thing. And this is much smaller than this. So this thing is exponentially dropping with time. So different ways of thinking about it. My noise is exponentially growing compared to my signal as I go to late time. And you see this in the data. You plot it, you plot what's called the effective mass, which approaches the ground state energy with time. And you get some excited state fall off, and then your error bars go like this. I mean, it's crazy. It's just, and if your signal is out here, you're screwed, right? So what we want to do is make our signal, we want to make it go to the ground state very, very early in time so that we can actually see it. And this is even worse if you want to go to larger numbers of particles. It grows exponentially with the number of particles too. So if you want to do 2 particles, now you've got this. And it just blows up in your face. So this is the main reason why nuclear physics is hard on the lattice, but this operator engineering is one of the ways that we get around it. Another way, which I'm not going to talk about, I'm done. So another way of formulating nuclear physics on the lattice that helps with this problem, I just want to put it out there. It's called the HAL QCD potential method. And rather than getting spectra and plugging it into Lucier, which Andrew's going to talk about, to get phase shifts, they compute something like a wave function, put it into a Schrodinger equation, and get a potential out. And I don't have time to go into it, but it gets rid of some of this signal-to-noise problem. But there are other caveats that you have to put in there, some approximations you have to make. But this is another thing on the market that you should just be aware of for calculating multinucleon properties on the lattice. And with that, I will be done.
Okay, are there any questions?
Hi, Anne. I'd like to thank for your lecture. I have a naive question. When you compute some quantities like blue balls, is the same structure?
Yeah, so if you want to look at glue balls, then you have to have an operator that contains the gluon fields rather than the quark fields. So you might compute something like a plaquette operator. We saw this plaquette, and then annihilate it, something like this. So whatever, these operators are going to be some products of gauge links that are gauge invariant. So if you take a trace, you get a gauge invariant object. So yeah, those are the kinds of things that you might look at for that.
Thank you.
Uh-huh.
Any more questions?
The problem with the chiral symmetry, can you talk more about when it's necessary to get the chiral symmetry in the lattice? So I'm thinking if you get lower temperatures, or I don't know if you're what the case.
Yeah, so a situation where it might be very important to have chiral symmetry on the lattice. So I didn't talk about things like matrix elements. So I could do something like create a proton at 0 and then stick some operator in here that tells me something about the proton, right? Like maybe it's an external axial current that tells me about the axial content of the nucleon. So chiral symmetry, what does chiral symmetry do? It tells us that certain operators which do not obey chiral symmetry should not contribute to such objects. So if I had an operator, I'm trying to think of an actual explicit example, and I can't off the top of my head, but these operators also are never exactly what we want them to be. It can be something like a QQ bar going into here, but you have to renormalize these operators because, again, they're not the exact quark operators in the continuum limit. And as you renormalize an operator, it might mix with other operators that are higher or lower dimension that maybe you don't want. So if there's a lower dimension operator that's forbidden by chiral symmetry, but chiral symmetry is broken on the lattice, you might get contributions from that you don't want. So that's the best case I can think of where you really need chiral symmetry. Domain wall fermions, which solve the chiral symmetry problem, help you because remember that Szymanczyk expansion that I talked about, where I said the lattice errors, so SLQCD plus A right, so we have a whole host of higher dimension operators. When you have exact chiral symmetry on the lattice, this operator goes away. So your errors come in at order A squared, and that helps you a lot. So, you know, it's not the end of the world to break it. People use Wilson fermions all the time because they're faster than domain wall fermions, but you might have to go to finer lattices. So it's like which one wins? It's not clear. So everybody does different things, and we just make sure we all get the same answer.
I have another question. It's not the topic of today, but it's possible to use lattice to solve things out of the equilibrium, something like solve Boltzmann equation and something like that, because they are using this relation, the temperature with the time. So I heard about something like Boltzmann, Lattice, something like that, but I never go see that.
Yeah, so in Euclidean time, the most straightforward things to get are equilibrium quantities, right? If you want to go to out of equilibrium quantities, you need either Minkowski time or some other workaround. So like scattering is a dynamical process. We get around that by getting finite volume spectra, plugging it into a Lucier formalism, and getting dynamical quantities out of that. So people have come up with methods for extracting dynamical out of equilibrium quantities from these things, and it's kind of like a Lucier workaround. I think they use like an actual spectral decomposition with time, and you relate it to the finite volume physics that you get. I can't write down an equation off the top of my head, but
Thank you very much.
yeah. So if you compute the pion, yeah. This is your pion correlator. The noise is just 2 pions, but you take the square root to get the variant, or to get the sigma squared. So it's constant. And this is, so it's constant as long as the U and D quarks are degenerate. And that's because this operator is positive definite, because it's a Q dagger state. If you have a kaon, where the masses of these two are different, the lowest energy state will be the 3 flavor singlet mesons. And there's a triangle inequality that says that, let's see. How can I write that? Yeah, so it basically says, so this is S, say, and U. This guy is always less than or equal to this guy squared. And the pion saturates this limit. But the more different these quarks are, the bigger your signal to noise problem is. It's still less than the proton.
When you, there are some errors related to the fact that the spacing is non-zero and the volume of your simulations are finite. And one of the methods to go around this issue is extrapolating to the continuum using different lattice spaces and things like that. Is there a way to do something similar regarding that problem with large T's to try to go around that signal issue? That signal and noise issue?
So essentially, that's what we do. We have the correlation function at all t, and we fit it to a sum of exponentials so that you don't have to go all the way out in time. But that's essentially extrapolating to infinite t, is
okay.
fitting to this form.
Okay, thank you.
Any further questions? All right. So thank you very much, Amy. We meet again at 2 o'clock. Thank you.